We all live in an era of big data. Every day there is an enormous amount of data created by users all over the world. Hence, what we do with this data, how we collect and store it, filter and use it, will affect our analytics and prediction models. Professor Niv Ahituv has dealt with the innovative technology in education throughout his entire career. Niv Ahituv is a professor emeritus of College School of Management at Tel Aviv University, where he served as the dean as well as the vice president and CEO of Tel Aviv University. In 2005, he was awarded a Lifetime Achievement Award by the Israeli Association for Information Technology. Professor Ahituv represented the Israeli government in UNESCO on issues related to ICT. In his talk, Professor Niv Ahituv describes the grid of data cycle and portrays the transformation of data in the process of decision-making. He will demonstrate how to build academic programs of data sciences and present a typology for these academic programs. So let us invite our keynote speaker to start his talk. Please keep in mind Q&A can be written in the chat box during the talk, and we will address them after the talk. I'd like to invite Professor Niv Ahituv.
It's a pleasure to be here in the HIT for this very important conference on grid and data science, which are kind of the hot issues in academic life today. I'd like to relate the data science to the notion of grid. The grid and the data science are now handled by a number of committees in Israel. One of them was formed by the Israel Academy of Science, and it deals with how to introduce data science into every discipline on campus, from humanities to law to medicine and whatever. And the other one, I'm a chairman of a committee that deals with forming a new concentration area in high school from grade 10 to grade 12. And this concentration area will deal with information and data and will prepare its students to either to study in the university or to become a data analyst in the industry. So that's why I think I can provide you with some additional information about grid and data science. But let's start with two examples. The first one is what disciplines are related to research on global warming. If we were in a regular classroom or a regular auditorium, I would ask this question and ask you to give me the answers. But since we are in a non-regular situation, I'm asking the question, and I also list the results. So if you want to do some research on global warming, usually you need to have combination of climatology, geology, oceanography, zoology, botanic, geophysics, and more and more. And I didn't mention here all sorts of social science fields such as sociology, psychology, and the like. Economics, of course. So, in order to have all these disciplines working together, you need to find some kind of a common denominator. You have to integrate data. You have to find what are the definitions of data in different disciplines. Like someone can call something water, where another person called it H2O, and the third person called it Wasser, or whatever language you want. So integrating and synchronizing the data is a major problem. Now, how do we handle this? We have to find ways to collect, cleanse, integrate, and process data which comes from very many resources. Another question: which is very, very actual and contemporary. We have this corona, or what is called COVID-19, and we are fighting it. Now, in order to fight it, we need a lot of different scientific fields. I'll give you the list here. Again, I wouldn't ask the question because I cannot get the answers, but here is the list. We have medicine, we have genetics, we have biology, we have physics, chemistry, economics, finance, management, law, engineering, whatever. So it is almost impossible to use or to exploit all these fields if we cannot integrate the data and take out what is really relevant and process it and show it to the decision makers. So the notion of grid nowadays is essential to almost any scientific research. There's almost no one discipline that does not need data from other disciplines. Now, what are the problems with all this huge amount of data? Every day, I express, every day there are new 2.5 exabytes of data, which is a lot. It's a huge number. The capacity of communication increased by 30% per year, and the amount of information collected every year grows by 20%. Now, this is totally impossible to control unless you have some means, and all these means are related to data science. Now, there was a study which was published in the Harvard Business Review, and it mentions that most of the managers, 80% of them, do not use the data that they can use and prefer intuitive decision-making because they don't have the access to all this data, and they don't know how to analyze it and to visualize it and to use it. So no wonder today the most demanded profession in the industry is a data analyst. Data analyst is more required today than programmers, systems analysts, finance professionals, etc. And the disciplines that prepare data analysts to the industry is data science. Data science is today the entry ticket to the digital world. If you go to the digital world without knowing data science, you lose your way. It's like not knowing English in modern society. Now, who are the students that we have to teach today? We don't have to teach them the basic tools. You see here in this picture that in the upper picture, you see that every one of them knows exactly how to deal with social networks, how to deal with browsers, how to get data, how to distribute data. We don't have to teach them the basics of handling data. We have to teach them the principles and the more advanced tools that will help them to get into this digital world. So, what are the main principles of data collection? There are four major principles and they are arranged under the abbreviation FAIR, F-A-I-R. F comes from findable, that is, the data has to be the data has to be found somewhere, and if you don't find it, you cannot use it. Then once you find it, the next thing is to access it. If you don't know or if you cannot access it, it doesn't help you if you know that it is somewhere there. So A comes for accessible. Then once you have it, you have to share it with other disciplines, and we call this interoperable. It's not enough that I have the data. I have to show it to another colleague, which is in different disciplines, and both have to use the same data. So it has to have some definitions or metadata that will enable them to do that. And by the way, this is grid. And finally, the data has to be reusable, because in science, of the term of repetitive experiments, the ability to repeat an experiment or to check or to verify your result is essential. I mean, you can't do science without it. So you have to reuse the data. Otherwise, it's no use. So these are the 4 principles of data collection. And now we come to something which is very, very important, and that is called the data cycle. The data cycle is a cycle starting here in the picture from the upper left corner. And this is the cycle that every data passes through, and it doesn't matter in which discipline and for which purpose you use it. It's some kind of a generic cycle, good for everyone, whether it be a decision maker who wants to do some kind of a business decision, whether it be a researcher, or even if you want to cross the street, you have to pass through all this cycle. So briefly, it starts from the, as I mentioned, the left upper corner. It's defining the problem, defining the question that I'd like to answer, then identifying where we come the data to solve it, then collect the data, cleanse it, because it's usually a little bit dirty. It's not always 100% proof. Then you integrate the data from various sources. You do the retrieval, namely the data mining. You take the pertinent data and use it, and you leave the other data away. Then you do the processing, the analysis, and after that you have to show the results. Now, showing the results is not very simple. Some people like graphs, some people like tables, some people like text, and it also depends on the data. If it's not quantitative, you cannot use graphs, for example. Once you do the visualization, you give it to the decision maker or the researcher, and the researcher analyzes it and comes to a decision, makes a decision. Now, how do we close this loop? We close this loop by sending feedback to the same cycle in order to improve it in the next time and maybe later, to make it better and improved. Also, there is another task which is not part of our talk today, but I have to mention it, and that is called knowledge management. You keep this data, you keep the results in your own organization in order to manage it and to keep it for other times where you need it. It's like gaining experience. Like if a baby starts to walk and fall down, then get an experience and keep it in mind. So that's knowledge management, very simply. Now let's review every step or every stage of this data cycle briefly, because we don't have too much time. But we'll see, you have this, in this table, you see the name of the stage, then the description of the stage, and then the tools that we are using them. So the problem definition is defining the problem or the question or the target. And the tools are usually formulation models, quantitative models, hypotheses, or things like that. Then we have to find where is the data. That's identifying pertinent data. We have to look at statistical bureaus, international organizations like the United Nations and its organizations, databases, etc. Once we know where the data is located, we have then to figure out how to collect it from them. We have to collect it, we have to store it in our own so-called home, and we have also to cleanse it. We have, because the data, as I mentioned earlier, is not always clean. So we use communication technology, clouds, database management software, data validation tools, and the like. Then, data integration, which is really a big headache, because you get data from many sources. Each of them use different metadata, each of them use different data definition. You have to make sure that these various databases know how to speak, so-called, with each other. So you have to do a lot of integration efforts using conversion programs, indices, and if you cannot unite them, you use metadata, and via the metadata, you get into the different databases. Once you have all your data integrated, you do the data mining by filters, the retrieval techniques, and heuristics, and things like that. Once you have all the data that is relevant to your question or problem, then you do the processing and the analysis using algorithm, AI tools, machine learning, data processing program, very intensive use of statistics and things like that. Okay, we finished the processing. We have to show the data to the decision maker, be it a researcher in the university or a CEO in a big organization. So we come to the stage of visualization, where, for instance, for business, we have what is called dashboard. And for researchers, we have usually tables, graphs, dynamic show of the data, and things like that. One of the major tools is, of course, user interface, or UX, UI, as it's called. Then it goes to the decision maker with the visualization, and the decision maker has to make the decision using decision support tool, what if software. Many times they use simulation, and finally they come to a decision, and now we are in the last stage where the cycle is closed by sending feedback to the beginning of the cycle and keeping the knowledge which was obtained from all this cycle in the organization using all sorts of knowledge management technique. This is, in a nutshell, the cycle, and surprisingly, it is common to every decision-making problem, every research problem, everything. It's generic. Now, data science is the collection of subjects and methods that cover the whole data cycle. That is, if you ask someone what is data science as an academic discipline, the answer is something that gives answers to all the stages of the data cycle. Now, how to teach data cycle? We divided it, how to teach data science. We divided it into three layers, three levels. The basic level is what we call here type A. This is in order to produce a data analyst in the basic level, and that is they learn a little bit about programming, little bit about retrieval programs, and they can work in business or in the industry in a very basic kind of technician level. The major program is type B. This is an undergraduate program in data science, and it should provide an academic degree such as BSc or something like that. And I'll elaborate on this in a minute. And the upper layer, which is type C, this is for graduate students that they want to do PhD or a master's degree. And this is more sophisticated. It's a lot of algorithmics, a lot of deep learning, machine learning, etc. And this is usually given or offered in graduate programs and not in the undergraduate program. So let's concentrate a little bit on the graduate basic program, what we call here type B. It consists of introductory courses, fundamental courses, core courses, and focusing courses. I'm not going to read or even to explain every course because it's a lot. So you see here the basic structure, and I'll show you now a number of slides where the list of courses is written, but I'm not going to read each of them. You can have, I guess, the presentation at home if you wish, if you can ask the HIT, and then you can elaborate on each course. So here is the list of courses. Start with the introductory courses. You see here a little bit of programming, a little bit of mathematics, a little bit of statistics, very basic. These are the introductory courses. Then we have the fundamental courses, which is more statistics, more data management, and a little bit of algorithmics and complexity. Then we have the core courses, which is, again, more complex statistics, distributed architecture and clouds, more programming, more data mining, artificial intelligence, which means machine learning and deep learning. This is really the top of the top of the program. And at the end, each student has to select a certain area of focus. For instance, someone wants to go to fintech, he'll learn more about, he or she will learn more about finance application of data science. If someone wants to go to health industry, then learn more about medical applications, etc., etc. So this is basically the undergraduate program, which should last over 3 years. Now, last but very, very important, the mandatory introductory course to every student on campus. The idea is that every student that enters a university or a college will have an introductory course, mandatory, in data science. Why do we need it? Because this is the entry point to the digital world. So today, students has to go to a college or university with knowledge of English. Similarly, the student has to go to the university or college with a knowledge of data science. It is not very deep, it's not very complicated, and we suggest that it will be mandatory for every student, from the humanities to law to management to social science, and of course for medicine, engineering, and biology and whatnot. It's a mandatory course. The course is divided into two parts. The first part is generic, and it's common to everyone. It relates to, it explains the data cycle, it explains types of data like numerical, alphabetical, etc. It reviews some of the basic tools that everyone should know, and it also gives some kind of judgment tools, like how to critically evaluate the data. You get a report. How can you tell that it is true, that it is okay? So some kind of critical evaluation, and finally, the ethical and privacy problem related to data. Every student has to be aware of ethical and privacy problems. Now, the second part of the course is different for each discipline. One it relates to basic tools related to the discipline. Like a student in medicine will learn different tools than a student in law or student in humanities. Today, there is already a concentration area which is called digital humanities, where we learn usually to analyze texts and things that are usually not quantitative. So we suggest that every student will have to take such a course upon entering to a university or to a college. This is basically the main message that I want to impart to you. If you have any questions, you have my email address right here. You can write to me. I'll send you the presentation, and I'm prepared to answer some questions. And I hope the message will advance science and industry as well. Thank you.
Thank you, Professor Ahituv. We actually have one question from one of our participants. Hello. Who's asking, in designing this data science program, do you believe we need to expose students to ethical and legal issues that result from the acquisition and processing of big data? And do you believe it is our role?
Yeah, sure. As I mentioned in the one before the last slide that I had, one of the issues that is common to all the students studying data science is ethical and privacy problems. And it certainly relates to big data and how to deal with that, how to make sure it is not linked to other places, and of course, how to make sure that the data is not abused for purposes not related to the research or the decision problem. So, I mean, I think this is really basic in the Type B program. It's a whole semester course about ethical and privacy problems. In the mandatory introductory course, it's one of the issues.
Thank you so much, Professor Niv Ahituv. Thank you very much for being with us today.
Thank you. Thank you.
When I'm not hosting events, I mostly work as a psychodramatist, which very roughly means that I treat people in a group or private setting using action therapy tools derived from the world of theater. I work with people from various backgrounds, which are remarkably different from one another. But through my work, I find that all people have repeating human patterns, a repeating human grid, a common grid of pain, fear, anxiety, and other friends that with proper understanding and care can bring us closer together and expand our ability to learn and be with ourselves and with others. My goal as a therapist is to widen our hearts and resources, to connect, to expand, and find inspiration in one another's inside grids. I'm sure that as we delve deeper into this conference, we'll find interesting things about ourselves and our own fields of expertise. So, what's next? This conference will be divided into 4 sessions. Each session has its own main topic and 2 lecture rooms. In each room or duet, there will be 2 lectures, one following the other, that will take place simultaneously. You can choose which one you choose to attend by pressing the links in the chat box. At the end of each session, we will present the topics, the lectures, and the links for the next session. We will be in both rooms to answer all of your questions via the chat box. You will be able to move from session to session through the website of the conference by clicking on the session you wish to attend. After the second session, we will all get together again for a prelude and visit to the Gridded Fabrications digital exhibition at the Vitrina Gallery. I will not be here alone today, so I'm pleased to introduce you to my co-anchor in this conference, my date for this duet, Miss Rachel Wolfarth. Hello, Rachel.
Hi, good morning. Good morning. It looks like it's going to be a fascinating day today.
Absolutely, already started in a fascinating manner. So those for Duet A, please stay put. And those for Duet B, you'll find the links in the chat box. And I will see you soon.